Okay, this is CS50, week 7, lecture 0. So, if the clicker works, did you guys like the music that we were playing earlier?
Yeah.
Anyone recognize it?
Zelda.
No, yeah, Zelda music, exactly. This is the Triforce, as you probably know. And you're also probably wondering how this, what is your clicker?
I'll be quick, man.
How this links to CS50. Well, we're not actually going to be talking about Zelda or playing Zelda today or anything. But we are going to be talking about this Triforce symbol. Now imagine I decided to cut out a triangle from each of those small triangles. Notice what happened. Each of these little triangles looks like a Triforce. So now we have 3 Triforces in the same shape as we did before. Do it again. We can keep going. Again, each of these small Triforces looks like a smaller Triforce. And what we've created here is a fractal. And you guys have probably seen fractals in math before. The idea of a fractal is a repeating pattern. And the core part of that is the fact that it's self-referential or self-similar. As in, each of these small parts looks like a zoomed-in version of the same thing. This is another fractal that you've probably seen. This is a Mandelbrot set, and this is some function on the complex plane which makes these nice colors. And this is a mathematical fractal. Again, the same concept of self-similarity and repeating the same pattern again and again. As you can see here, like this little circle is the same as this circle, but bigger. The core idea of fractals is recursion. And recursion is a word that means a pattern that repeats within itself, and something that's self-similar to itself. So if we now go and look at this video, we can see some cool thing about fractals, the fact that they come up in nature quite often. If we play this video, we can see that we're going to build the Sierpinski's triangle, which is that Triforce fractal that we had before, from seemingly random dots being placed on the screen. So let's enjoy this video. Kind of see the shape starting to form already. So look at that, from seemingly random placement of dots through some algorithm, we've managed to generate Sierpinski's triangle. And this just kind of shows how ingrained fractals are into our nature and how they appear everywhere. Like just from this simple pattern of walking halfway between the dot and the line, we get a very clear image of Sierpinski's triangle, which is actually quite a nice image. Like it looks nice. Now, again, all this stuff is cool, but it's not particularly useful. Mandelbrot himself described fractals as beautiful, damn hard, and increasingly unuseful, which they are. There's really not any direct use of fractals, especially for us as computer scientists. What there is a use for, though, is recursion. Now, let's look at this function here, n factorial. We know the factorial function. We've seen it before. The factorial of a number is that number multiplied by the integer before it, all the way down to 1. So this definition of factorial, n times n minus 1 times n minus 2, blah, blah, all the way down to 1, is a perfectly valid definition. If we look at 8 factorial, it goes 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But if we look a little closely, we can see that this part, the part that's white right now, the 7 times 6 times 5 times 4 times 3 times 2 times 1, is exactly the same as 7 factorial. So 8 factorial has 7 factorial in it. And that means we could rewrite our definition of 8 factorial as being 8 times 7 factorial. This is an example of recursion. In defining the factorial of 8, we've used the factorial of 7, self-reference. Again, the factorial function is referencing itself. That's recursion. So we could go and extend our model of our definition of factorial to also be either that, or you could use n factorial equals n times n minus 1 factorial. So let's try that for a second. Let's say we take the number 4 and try and do 4 factorial using our second method. Okay, that would be 4 times 3 factorial. 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. 1 factorial is 1 times 0 oh, no, that's not right, because 1 factorial we know is always 1, because it has to stop at 1. Otherwise, this factorial function would just keep on going down, lower into the negative numbers, go below 0, go minus 1 factorial, and we don't know what goes on there. We know that 1 factorial is always 1. It's just 1 on its own. So we specify that in this function, except when n is 1. In that case, we just say that n factorial is 1. This is an example of a base case in recursion, a case that you stop at. You don't keep going back into infinity like you would see in this picture. And it doesn't look infinite because the detail on the screen runs out, but this picture is kind of an infinite recursion, what happens when we don't define a base case. Now, factorial, useful for mathematics, somewhat useful for computer science, but the idea here really is to generate some kind of algorithm using recursion. Now let's say we want to empty a basket, right? This is my basket. We're a bit short on resources, so this is the best basket we could afford. And I have some objects in here. And one way I could empty them is iteratively. I could say, first remove the first object, then remove the second object. Yeah, do that. Have you, yeah, exactly. After removing a duck, we check if the basket is empty. Not empty, so we remove another thing. Not empty, remove another thing. We keep iteratively checking if it's empty and removing things. This is kind of like a while loop, sort of. It's an iterative process. Now the basket is empty and now it's done. But our algorithm for this emptying basket is kind of really long. It's the same thing repeated again and again. Of course, as we know, we could have shortened this into a while loop. But here, what we're doing is an iterative process, repeating the same step again and again on the same level. We could redefine this algorithm in a certain way if we move to the next slide. We could say that, okay, we remove one object. First we check if the basket is empty, which it's not. In that case, we remove one object, and then we empty the basket. Now here's the difference. In emptying the basket, I've said, I'm going to empty the basket. That's recursion. In defining the function of how to empty a basket, I've said I need to empty the basket. So if we look at our pseudocode here, on line 4, we say, on line 3 we say remove one ball, and then we empty the basket again. How do we empty the basket? Oh, we repeat the same steps. If the basket is empty, we're done. It's not. So we will remove one item, and then empty the basket. Okay, how do we empty the basket? Again, we go back to line 1 because we're, again, emptying this basket on a deeper level. It's like a recursive call to empty the basket. If the basket is empty, done. The basket's not empty, so again, we remove a duck. Then we empty the basket. Again, we keep recursively doing this now. And for this specific algorithm, the recursive definition looks basically identical to the iterative definition. And this is something you'll notice as you keep getting deeper into computer science, is that anything you can do with iteration, you can do with recursion. But in some cases, it might actually make more sense to use the recursive method. For factorial, it's nice, but not necessary. But if we go to the next problem here, what if we were sitting at the back of a lecture theater and we wanted to count the number of rows in front of us? So I could do this iteratively with the help of my teaching fellow. if Will could go to the back of the lecture theater and stand on the top stair, he could say, start the count of rows at 1, move down 1 row, and then add 1 to the count. So do that. Now there's 1 row. Move forward again. 2 rows. Move forward again. 3 rows. 4 rows. 5 rows. 6 rows. 7 rows. So he's counted the number of rows in the lecture theater by starting at 0 and then adding 1 each time he moves down. It's an iterative process. As we can see here, we move 1 row down and we increment the row count, and we keep repeating this again and again. What if there was a better way to do this that didn't require Will to move? I would ask all of you to line up on different rows so that we can demonstrate this new method with Will at the back. Cool, cool. Now, Will, sit behind Rob, and what I'm going to ask you to do is, in order to count the number of rows in front of you, ask Rob the number of rows in front of him.
How many rows are in front of you, Rob? I don't know, but that's how many rows in front of you?
Ah, exactly. Beautiful.
I don't know how many rows in front of you, Alex.
1.
Nice. Now, what are you going to tell Rob?
There are 3.
Okay, that was kind of... Okay, yeah.
4 in front of me. There's 5 in front of me.
Exactly. So what you've done here is you've asked him, he's done the same thing. He's asked Matt. Matt's asked Alex. So you've done this recursively. Each person has added a new call to how many rows are there by asking the person in front of them how many rows are in front of them. And the base case that we talked about here is Alex, because Alex doesn't have anyone in front of him to ask. So he just reports that there's 1 row in front of him. And obviously our pseudocode is slightly different here because we could have done this with the full every row having a person in the lecture theater. We could have, the person at the front who was sitting here would have said 0 rows in front of me. So that's why my pseudocode says that. But essentially, the algorithm is recursive. Whatever Will did, Rob has done the same thing. He's done the same. It's a self-referential algorithm. And these kinds of algorithms are going to come up a lot in computer science. We're going to be talking, if you remember, we talked about the binary search with the dictionaries. That's going to come up again. We're going to talk about some sorting algorithms down the line. But right now, all we're trying to do is introduce you to this concept of recursion. And that is essentially it. This has been CS50DC Week 7. Thank you.